Hey, welcome back, my little bottles of hot sauce. We are going to talk about your favorite thing in the whole wide world. No, not fractions. No, not puppy dogs. Word problems. And I know you love yourself a spicy word problem. Every day before bed, you say, Mama, can I please have a warm glass of word problems? She says, get yourself to bed. But anyway, I digress. We're going to talk about some application problems. Pay no mind to what you eat before bed. Yeah, word problems. We're going to do them. You're going to love them. Let's go. Before we talk about word problems, though, Barton, please. I know. We gotta have a little conversation about some of these things real quick. Some similar triangles. There is a fact about trig ratios and similar triangles that some of you may have just noticed on your own, but I just want to point something out to you. So first of all, come on, Barton. First off, a similar triangle or a set of similar triangles are two triangles where all of the angles, here let's double bore, match, but the sides are not the same length. They are proportional to each other, but they are not the same length. All the angles are the same, but not the sides. So that's what a similar triangle is. Let's pick this triangle here, for example. Let's just make these some nice numbers. Let's say this is 4, this is 3, and let's pretend this is twice as long. Let's say that's 8. If I look at this is an angle. We know this angle. Pretend. I don't know what angle this would actually be, but we could solve for it with the information on the screen. But let's pretend you know it. Let's set up the trig ratio that we can for here. So we know the opposite side, and we know the adjacent side. So say it with me. What's the trig ratio that we're going to use for this? Tangent. Good job, kids. This is tangent of theta equals 4 over 3. Now, recall when we learned the unit circle and all that stuff. If I ask you what is sine of 45 degrees, this is a constant value. This is radical 2 over 2. It doesn't matter what triangle you're looking at. This is always the same value. If you look at cosine of 30 degrees, this is always going to be radical 3 over 2. If you have an angle, cosine or sine or tangent of that angle will always be a set value. Meaning, if I know the opposite and the adjacent side, as long as this angle doesn't change, these two numbers should always reduce to this same ratio of 4 over 3. So, because this is also theta, we could set up another trig ratio. Let's say we want to figure out what this side is here. Let's call it x. Okay, this is the adjacent side, of course. This is still the opposite side. We would set up tangent of theta equals 8 over x. Because tangent of any angle is always equal to the same ratio, tangent of this theta has to equal tangent of the same theta, even if we're looking at two different triangles. Comprende? So because this tangent of theta equals 4 over 3, this tangent of theta should also equal 4 over 3, and we can set their ratios equal to each other, and that lets us solve for x really easily. So if I double the top, I should probably double the bottom, right? X equals 6. So you need to know if you have similar triangles, then their trig ratios should be equal. If you have sine of theta equals 4 over 5, and then you stretch out that triangle, the ratio of its opposite side to its hypotenuse will always be 4 over 5, meaning the opposite side will be 4/5 of the hypotenuse every single time. So if the hypotenuse was 5, the opposite side would be 4. If the hypotenuse was 15, the ratio should still hold, and this would be 12, right? The ratio should be maintained for any given angle. Okay, let me show you why we care. Let's look at this first example. I know, I am an artiste. I hand drew this, and I gave this lady a banging blazer. Check that thing out, it's so tight. I gotta be really careful here not to hit the clear ink button though, because otherwise it's gonna erase this. Check out that shadow, look how buff she is. All right, so example 1. It says we have a 6-foot tall woman standing 12 feet from a lamppost, and she casts an 8-foot long shadow. How tall is the lamppost? So if this sentence or 2 sentences doesn't make a whole lot of sense, check this diagram, okay? This lady is standing 12 feet away from the lamppost. Her shadow is 8 feet long. She is 6 feet tall. We want to know, how tall is this lamppost? Okay, so let's observe something about these 2 mini triangles. The lady, her shadow, and this beam of light make a right triangle. There we go. This right triangle, because it is inside this bigger right triangle, these are both 90. And then because these angles are literally the same angle, we can say that these 2 triangles are similar. Okay, that should be something that you, I don't know, learned a long time ago in like geometry or something. Come on, why did my triangle break apart? All right, so we've got these 2 similar triangles. Let's go ahead and label the sides of these 2 little triangles that we have. And we're going to use this fact that trig ratios of, let's back up. Oops, back forward. Of similar triangles are equal. Okay. So we'll call that theta, because they're the same angle. Okay. We know for the little triangle, the woman, right? Woman, shadow, light ray. She's 6 feet tall and her shadow is 8 feet long. Now we want to know how tall is this? What's h? Well, we don't know the hypotenuse. We don't have a way of calculating that yet. But we can see she's 12 feet from the base, and then the shadow goes 8 more feet. 12 plus 8 is 20. So this whole bottom piece here, that's 20 feet long. So now, even not knowing this little angle here, we can set up a trig ratio. Because we're going off this angle, it would be opposite and adjacent. So this could be tangent of theta equals 6 over 8. And we could reduce that to 3 over 4. Because this is the same angle as this, tangent of theta, for this one it is, let me move this, sorry, I don't like where I put this, h over 20. Because it's tangent of the same theta, it should equal the same ratio, equals 3 over 4. All right. So now you can probably tell, because you just multiply 4 by 5 to get 20. So we multiply 3 by 5 to get h is 15 feet tall. But for argument's sake that this isn't a nice number, the way you would solve this is cross multiplying. You would do 4 times h equals 3 times 20. Divide both sides by 4. H equals 15 feet. An apostrophe is the universal symbol for foot, but anyway, cool. So you're gonna have a problem like this. It's probably gonna be a lady standing in the shadow of a lamppost, but, you know, it'll be cool. All right, next example. All right, so example 2, it says the machine shop has a radius of 24 inches. Nah, the machine shop has a 24-inch radius metal disc. Reading is hard, you guys. And needs to drill a 3/8 inch hole every 30 degrees, 20 inches from the center. Okay. The CNC machine, I don't know what this stands for, but basically it's a machine that cuts stuff for you or drills holes where you need it or cuts stuff into certain shapes. It's a cutting machine. The CNC machine only accepts instructions in the, this should say form. Holy smokes, proofreading, you guys. In the form of X and Y coordinates, though. Okay, so if I want to tell it where this is, I need to say however many inches this way, however many inches this way. Find the ordered pairs marked on the diagram. So the issue here is we have a disc and we want to cut holes into it at equal angles at the same radius. Okay. This is actually a coordinate system. Someday you're going to learn about these sweet things called, polar coordinates. Instead of X and Y, you're going to have R and theta. Right? So it'll tell you how far out to go and then how far to spin. It's cool. They're very interesting, but unfortunately, you bought the cheap CNC machine, not the $10 trillion CNC machine. So you have to tell it X, Y, and it's in R and theta right now. So we need to figure out where is this hole and where is this hole in X and Y coordinates. We're just going to do one for the sake of making this video not an hour long, but we could get this one if we really felt like it. So here's what we want to do. This angle here, it says we want to do it every 30 degrees. So this is 30 degrees. Okay. We know that this is 20, and we want to know where this thing is. So here's what we're going to do. We're going to make a little triangle. Notice that this X is not all the way at 20. Okay. So what we're going to do is we are going to find the X and the Y at 30 degrees by using sine and cosine. So you should be getting some very eerie unit circle vibes right now. But unfortunately, we can't just say, oh, 30 degrees, this is radical 3 over 2, this is 1/2. We can't say that because this is for the unit circle. This is not one radius, or radius equals 1 unit. This is 20 units. So what we have to do is we have to take advantage of the fact that we know this length is 20. So you can see on this triangle, we're looking for Y and X, but we know the hypotenuse. So we're going to just set up some trig ratios. So let's go ahead and find the X first. So X is the adjacent to this angle, and I know the hypotenuse. So which trig ratio uses adjacent and hypotenuse? Oh, cosine. So we're going to do cosine of 30 degrees equals our adjacent, which is the missing side, which is X, divided by our hypotenuse, which is 20. So we know cosine of 30 from the unit circle. Think to your unit circle. What's cosine of 30? I just wrote it right here and erased it. Oh, it's radical 3 over 2. That equals X over 20. Now we need to solve for X. So we're going to multiply both sides by 20. To get rid of this, divide by 20. So these cancel, and we get X equals 20 divided by 2 is 10. So this is 10 radical 3. Notice that this is just the coordinate we thought it was from the unit circle times the hypotenuse. Whoops. Let me make that a little smaller ink. There we go. 10 radical 3. So we can guess that this is just going to be sine times the hypotenuse. So sine was a half times 20 would be 10. But let's just verify that to make sure that we're not, tripping or something. So if we want y, this is the opposite side. So we're going to use sine now because opposite, and we know the hypotenuse. Even though we know x is 10 radical 3, I wouldn't want to use this number in a calculation. So I would stick to using this nice, easy 20 number. Because you know this one exactly. This isn't rounded. If you type in the decimal, it is. But if you leave it like this, it's not rounded. You could use x and the opposite side and use tangent. But I like 20 a lot more than I like 10 radical 3. So opposite and hypotenuse, that would be sine of 30 degrees equals y over 20. Sine of 30 degrees is something we should know from our unit circle. This is 1/2 equals y over 20. And just like we thought, it is 1/2 just times the hypotenuse times 20. So y does equal 10. But it's nice that we verified it. Okay, let me show you just a little bit about this one, just in case. So notice we don't really have this angle here. We know this is 30. So what you would want to do is just say, oh, well, this whole thing is then 60 degrees. And then you repeat this process with 60 degrees here. Draw a bigger triangle like that. And you can probably guess that these just flip because at 30 degrees, it's radical 3 over 2, 1/2. At 60 degrees, it's 1/2 radical 3 over 2. And you'd be right. They do just flip. So it'll be 10 radical 3 as the y. They flip for 60. So there we go. All right, we've got 2 more example problems just to get a nice wide range of all the weird stuff that's out there. There are so many word problems we could do, but these are just some nice ones I found in the book that I thought, you guys would really enjoy. You go, you know what? My math teacher fed me some spicy math today. I'm very grateful. All right. So now it says we have a tapered shaft, don't giggle, that has a diameter of 2 inches, right there, diameter all the way across, at one end and is 6 inches long. So this way, I should have marked this. This whole length is 6 inches. Okay. If the shaft tapers outward at an angle of 3 degrees, find the diameter of the wider end. Okay, so let's figure this out. Okay, unfortunately, you can't just kind of figure it out like this, right? You can't, that's kind of weird. So here's kind of what the trick is. The trick is erase this. We don't need that. Let's get a bigger eraser. Okay. So can you guys see that this kind of makes a triangle? A very long, narrow triangle? That's intentional. Okay. So this is a right triangle, right? We know a bunch of trig for right triangles. How handy is that? So we have a triangle that is, I'm going to exaggerate this a little, like this, and this is 3 degrees. Okay. Now we know from here to here is 6 inches, so it's telling us this horizontal length here. This is 6. What we want to know is this full diameter. We're not going to be able to find that straight away, but we'll be able to kind of infer it because we can use logic. So we know 6. We want this height here. So let's find this missing side length of our triangle. It's going to be really small. It's going to be, it looks like maybe a third of what I drew here, but this is exaggerated, not really drawn well. All right, this should be a lot skinnier. So let's set up a trig ratio. Here's our angle. This is the opposite side from the angle we know. This is the adjacent side from the angle we know. So we need to use tangent. So this is going to be, let me make this a little bit bigger, tangent of 3 degrees equals our opposite side divided by our adjacent side. Now this thing, we're going to just go ahead and throw straight into our calculator. So tangent of 3, whoops, if I could type, tangent of 3 degrees is 0.052408 equals x over 6. And now we're going to multiply both sides by 6 to get the x by itself. Okay. Times 6. So x equals 0.314447. Okay, wonderful. So now what we have found is this tiny length right here. So now we need to think about the geometry of this problem and kind of do a little bit more math. Well, the way that this is drawn, we can see that the cone? Not cone. What is this shape? A cylinder. This cylinder is drawn. So they're kind of implying to us that this thing here has a diameter of 2. Well, we just found this thing. That's this little chunk here. But we have that same little chunk on the other side. So let's start by doubling this to get this chunk plus this chunk, because we have 2 of them. So we're going to multiply by 2. So if we multiply by 2, that is 0.628893. And then we're going to just add that to 2. So plus 2, boom. This is the diameter of the other end of our tapered shaft. In inches, of course. Cool. So set up a little triangle to find this length. Double it because it's on both sides. And then add it to the inner diameter. Cool. Last one. From a 100-foot tall observation tower, the Coast Guard gets an SOS call from a ship in distress. The Coast Guard goes to the top of the tower and spots the ship offshore and measures the angle of depression of 4 degrees. How far offshore is the ship? So angle of depression means if you look straight horizontal and you measure how far down you're looking, it's that. It's not like the slippery slope that leads to you crying yourself to sleep. It's not that angle of depression. It's a different one. Okay? So what we need to find is how far offshore is the ship. So we need to figure out this length right here. Okay. So they've kind of set this up in a weird way. They said this lighthouse or this observation tower is 150 feet tall. They've kind of implied to us that the end of this triangle is the same height as this. So you need to realize that this 150 needs to go over here. Okay? And then this is super easy. We're just going to set up a trig ratio now and then solve for x. So again, the angle we know is this angle way back in there. Okay? The opposite side is this 150. And then there's our hypotenuse at the angle. So this is our adjacent side. So we're going to use tangent yet again. So tangent of 4 degrees. Whoops, not 40 degrees. Come on now. Equals opposite over adjacent. Okay, so let's figure out tangent of 4 degrees really quick. Actually, let's not, because it's a weird decimal. Let me show you a trick really quick. Let's leave this as tangent of 4 real quick. And we're going to do some manipulations. Kids usually struggle with the fact that this x is on the bottom. So let's get the x not on the bottom. To get this x out of the denominator, we're going to multiply both sides by x. Okay, so these x's cancel. On this side, we have just 150. And here we have x times tangent of 4 degrees. Now we want the x by itself, and it's being multiplied by the tangent of 4 degrees. So to get rid of this, we need to do the inverse math operation. We're going to divide by tangent of 4 degrees on both sides. Okay, so these cancel, and now we have just x equals 150 divided by tangent of 4 degrees. And then you can type this thing into your calculator and it'll give you your weird decimal. So this is going to be 150 divided by tangent of 4 degrees. X equals 2,145.1. And let's be honest, that 0.1 is not really that important. But, you know, we found it, so we'll put it feet. All right, there you go. So that's word problems. Really, you're just looking for triangles, and then you're going to try and set up some trig ratios. Find whatever you're looking for, put that as a variable, and then solve your trig ratio for the variable. The hardest part is going to be figuring out what trig ratio you're using. Problems like this, even when you're done finding the x in the trig ratio, sometimes you have to do a little bit extra math just to get to the finish line. And then remember, if you have similar triangles, tangent of theta always equals the same ratio. So you're going to just set your ratios equal to each other. 6 over 8 equals h over 20, and then solve for h. Okay. Thanks for watching. I hope this was helpful. If it's not, you know where to find me. Go ask me some questions, you know. Otherwise, I'm just going to sit around and make more lecture videos. I'll see you guys next time.